Greetings, everybody. I'll be presenting this lightning talk about my current research project. So I have finished my, let me introduce myself first. I have finished my master's degree in the Santa Catarina State University in Brazil. I'm currently unaffiliated to any university, but I have been going there since then. So I'll be presenting about the CPS calculus for now. So as Michel has been talking the past few days, the CPS lambda calculus in CPS style is commonly used as intermediate language for functional programs while in the compiler pipeline. But when studying a CPS translation, the process of translating a program written in direct style as a programmer would type it into a program in CPS style where the compiler can handle it, it's common to see the translation given into the same language. So we translate, for example, from the lambda calculus into the lambda calculus itself. It's being presented, the CPS calculus, which is meant to be used exactly as the target of such translations, So you can translate, for example, instead of translating from the lambda calculus into the lambda calculus again, you translate into the CPS calculus, which can only represent programs in CPS style. And it's also possible to see it as a common ground for both the lambda calculus and the P calculus. The common syntax subset of both represents the CPS calculus. One of the points of doing so is to extend the curry-Howard correspondence to intermediate languages. For example, the CPS calculus, which can be used as a common intermediate language inside a compiler, corresponds to the implication-free subset of propositional logic. So I'll just give a small overview of the calculus. It's rather simple as the lambda calculus is. So you have just a jump construct. You can jump to a continuation, giving a set of arguments. And you can bind a continuation inside another term. So in order to see the intended meaning of these constructs, we can give translations, syntactic translations, both into the lambda calculus. You see the jump is just an application. And the bind structure represents the mutual binding of a continuation on the left side and the formal parameters for the continuation on the right side of the expression. If you're familiar to the P calculus, you can also see the same translation applied to it. So it's a common subset of both calculi. So of course, in the P calculus, we have a small restriction on the binding structure. A simple type system for it represents either a jump. There's only two inference rules. So if we have a continuum, which is a negation of chi, and we have variables that represent chi, we can derive a contradiction on the calculus. The same thing goes for a binding operation. It's just our goal here is always to derive a contradiction. We have to have chi in one side and the negation of chi on the other side. So for example, we have no types here for the inference rules. This judgment represents that given the context gamma, our terms entails a contradiction in the type system. So given the semantics of the calculus, it's based on 4 axiomatic rules. So we can always perform a jump to the closest continuation. So if we perform a jump to k with actual parameters x, given that we are bound to continuation k with formal parameters y, we can simply do the substitution rule just as the beta reduction, the lambda calculus. As in the lambda calculus, we have an eta rule that allows us to foresee a continuation. We have a simple garbage collection rule, so we can always remove bindings to continuations that are never used. And we have a simple structural rule that it's a little bit more notation bloated, but all it says here is that a term does not care about the order of the continuation. So if we have two binds here, k binding to m, and j binding to n, we can change the orders of the parameters here. So these four rules represent the semantics of the calculus as it was originally presented. We have an additional rule that says that we can merge continuations to the sum term. For example, since m is equal for both k and j, we can simply replace them for a single continuation. But it turns out this fifth axiom can be derived from the other ones. So we don't have to take it as a primitive axiom. So for a reduction operational semantics of the calculus, we have just a single reduction rule where we have a jump in the head position. We have follow a series of bindings. Given that they is bound for one of these continuations, we can simply replace the body, keeping the bound continuations there. We note here that this notion of reduction is sound with respect to the original semantics, and that it's not compatible. So, for example, as in the cal by value lambda calculus, you must have you have only a deterministic position where you can perform a reduction, always in head position here. So in order to find the redax on the CPS-calculus, you just look for a bound continuation in head position. Once this variable is free, it means we have no more reduction to perform. So one of the points of my research is to actually extend the relation to allow inner reductions. So for example, we can here consider a context and apply administrative reductions inside of the term, thus extending the reduction relation that's already present in written material. So we can as well, through this new reduction relation, remove unused continuations and perform the eta reduction as well. So what's the point of my research for now? I'm trying to show a few syntactic properties of the CPS-calculus. I'm doing the formalization in Cork, so the code is on GitHub right now, if anyone's interested in seeing that. And the main two properties I'm trying to show is the confluence in the strong normalization of the reduction. So confluence, the confluence proof is already finished. So this relation is confluent inside the CPS-calculus. And as the original reduction relation that I call a head reduction, that's a little bit more restrictive from the full reduction, it's a subset of it. So this would imply normalization of the original semantics. If we take the barbed congruence of both relations as it is defined, for example, calculus, these relations we consider. So what does this mean? Inner reductions inside the CPS term cannot change its behavior from external observations. External observers always see the same thing. So this allows, for example, the removal of administrative redexes inside terms to optimize a term in CPS-calculus inside the compiler. So we just have, okay, we get an hierarchy of not that important. And finally, I'll try to prove the full abstraction of the lambda calculus. So I'm trying to say that the translation, basically the translation is sound with respect to the semantics. I think that's basically it.
Oh, hello. Is everybody hearing me? Okay. My name is Guilherme Horta Alvares da Silva. I will talk about my history. I graduated at Computer Engineer at the Instituto Militar de Engenharia, Army University. This is me at left. This is my university near the beach. I liked very much mathematics competition. I was at Canada. I got the second place in statistics at the University of Ottawa. And here is I with people of Brazil doing international mathematics competition. I have done my master's in applied math in Fundação Getúlio Vargas, Rio de Janeiro, and there I have classes about blockchain, machine learning, algorithms, logic, and theorem proving. In Rio de Janeiro, I have classes with Philip Wadley about the programming language foundations in Agda at PUC Rio. Here is Philip Wadley. And this is the books that I liked when I have done my master. This book is Type Drive and Develop with Idris, that I learned how to make code with dependent types. It's very good introduction book. This book, The Little Type, is very good so too, because I have learned how to construct and destruct types using Py is a programming language like Lisp with dependent types. Optics by Example is a good book to learn some features about optics. It's good because Haskell does not have a lot of syntax circuits, but with some notion of category theory, you can solve this problem using optics. And this is the book Type Theory and the formal proof that I have learned in my master's, that it's very good introduction book, that he explains lambda cube, system F. Here's some websites that I like to study. From Lean Community, I have found Shena, that there are a lot of exercises in mathematics to do. I have done some real analysis in Shena. There are natural numbers game too. Software Foundations is a good book to learn some concepts about programming languages. And this book, Programming Language Foundations in Agda, is also a good book that looks like Software Foundation. My master thesis is a simplified version of Bitcoin implemented in Agda. I implemented most of core features of Bitcoin. I proved some theorems about it, and I used dependent types to have more elegant definitions. Here is my GitHub repository for someone who wants to see it. Here's some code about my master thesis. I defined what is an injection function. I define here what is a hashable. It's a type that has a hash. A hash is an injection function. And I define what is crypto keys, like what is private key, public key, and a signature. Private to public, so I can make a public key from a private key. If something is signed, I have a message, a public key, and a signature. I have a function that derives a proof that something is signed or not signed from a message, a public key, and a signature. And I have a sign function that I assign a function from a message, a private key, and I got a tuple of the signature and the message signed with a public key from this private key. Next steps, I am looking for a PhD in programming language and theorem provers. I enjoy a lot Agda, Idris, and Lean. My favorite language are these three. And some fields that I like it too is category theory, cubical type theory, algebraic effects, and thanks for the attention of everybody.
I'm David. Here's a picture. Hi, David. Hi, guys. Here's a picture of me because you probably can't see me currently. I'm a PhD student at Technical University of Darmstadt, which lies in Germany. And I wanted to shortly introduce you to what I'm working on, which is an embedded smart contract domain-specific language embedded into Scala. And there's some collaborators, David, Lisa, Sebastian, Guido, and Mira that I'm working with. Okay, what is a smart contract? And to answer that, we can go back a few days to our external guest lecture by Jamie, who already answered what is an AX2 blockchain. And his answer was basically the one thing that he wanted us to remember from his talk was, well, it's a partially ordered partial monoid. And I think that's actually a pretty nice answer. But the one thing that I want to focus on is the smart what's the function of the smart contract in the blockchain, and that it's all about the partiality, right? So we have our chains. For example, here we have two chains, which are sequences of states, and we would like to compose them. We would like to know whether they fit together. And this is the question of partiality, right? So not all chains can be put together to form a new chain. Sometimes it's not valid to compose them. And there are two styles to defining whether it's valid to compose the two chains. And the first style is the one from Jamie's talk about unspent transaction outputs, which is the style originating from Bitcoin, where we define whether two states can fit together by defining a function, a validator that takes two consecutive states and returns a boolean whether they fit together or not. And there's this second style, which is the style that's used in the Ethereum platform, where instead of composing states, we distinguish between states and actions. And it's an action that takes us from one state to the next. So to define whether it's valid to apply an action in a state, we instead write a function apply. Well, I call it here apply to model it. And this function basically takes the state, takes the action, and then returns the new state. And of course, it's also partial because not all actions are valid in all states. And Here's an example for a smart contract. This is a finite smart contract, so it's going to end after 5 steps, and it's accumulating state until it can do its purpose. And it's this one is about generating random numbers between 2 parties, A and B. And basically, we want both of them to be surprised about the random number that they're generating. So what they do is they first generate locally a random number, and they only and then in alternating turns in this smart contract, they're going to interact with the smart contract, and they're basically these 4 steps here. With we first initialize the smart contract, then A is posting a hash of its locals number to the smart contract, then B is publishing a hash of its number to the smart contract, then A is going to reveal its actual number, and the smart contract is going to check whether the hash of the number that it published previously matches the revelation of the number, and then B is going to reveal its number. And finally, the smart contract, having accumulated the hashes and the revealed numbers, can produce a combined number, which, because neither A or B knew the other number, will be a surprise. For example, you can simply just add the 2 local numbers to generate a new number. And if you would like to, oh, thanks. I'm always a bit fast. Okay, and if we were trying to write such a program for the Ethereum platform, then we were going to use the Solidity programming language. And if you read a tutorial on how to write a smart contract in the Solidity programming language, then you would be told, okay, there's this design pattern that you should use. It's the finite state machine design pattern. And it fits really well, this example program that we want to use here. Right, we have these 4 steps that are going to happen on the contract, with potentially 1 initialization step in the beginning. If you're wondering why there are 5 steps in this picture, where C is the contract in the middle. And basically, for each step, for each thing that the contract is then supposed to do, like accepting the hash, accepting the revealed numbers, and then combining them at the end, we're going to write 1 function. And then we have a global step counter that goes from 1 to 5, counting up. And inside of each of those functions, we're going to assert this function is only can only be called if we are in the right state, and then we go to the next state. And that is kind of this finite state machine, where we have these 5 or 4 different steps, one after another, that we're going through. And one thing that we can notice here is actually, well, this produced smart contract that we've just written, it actually looks an awfully lot like a control flow graph, especially if we look at the picture that I drew to visualize the whole thing. So the question here is, can we instead write a program that would produce this control flow graph? So instead of writing the finite state machine itself, we go 1 level up in our ladder of abstraction, and instead of having 4 different step functions, we define a single function that just executes the first step, then the second step, then the third step, then the fourth step, and then the last step. The problem here is we can't really write that in Solidity, because actually we are still only describing the contract in the middle, but we're kind of building something like a coroutine here. All of these steps cannot be immediately executed one after another, because we need to wait for input from the 2 parties A or B in the middle. We need to suspend the execution of the contract. And we can build that. We can try to produce a new language that has some like a yield keyword, where we can wait in the middle of our execution to do that. But actually, we should go 1 step further. Like, there's an additional question. Our program still only represents only the contract. But if we look at the whole protocol of our smart contract, there are actually also the steps that the parties A and B want to execute. And can we actually go 1 step further and write 1 program that encapsulates the whole protocol? And yes, we can also try to do that. And that's what I'm trying to do. Here we write a program now in the host language Scala. And we use this contract operator and this client operator, where if we enclose something in a contract bracket, it tells the compiler, okay, the thing inside of this bracket should be executed in the contract. And then inside of this bracket, we can escape from the contract execution and say, okay, but this part should be executed on a client, and the contract should wait until it's finished with executing. And then we can write the whole protocol in a single embedded domain-specific language for smart contracts. And then we need a compiler or a macro system, in our case, that takes this source program and then splits it up in all the individual parts that we're going through. And that's involving a lot of different techniques. Like we're first bringing the code into a monolithic normal form, then we're desuring it, then we're defunctionalizing it, and then we're generating the finite state machines that we wanted. We're also involving some serialization and deserialization. Then we have to translate the Scala code to Solidity code, and then finally you can run it. And this allows us to write our whole smart contract together with the parts around it in a single programming language and execute. Thanks, that was my talk. If you have any questions, raise your hand, say something, or we go to the next talk, or you just write it in the Slack channel.
Can you enumerate some reasons why Scala specifically was chosen as the host language?
Well, the first reason is probably that I'm using Scala before and I'm well versed with it, and also because we're using this macro system in Scala to manipulate the code, and it's always good to have some libraries, some things that are that you can use to build upon.
Okay, thanks.
I have a question.
Sure.
Any features in Scala that got in the way, so features that you wish you had, so to make your life easier?
Well, first I can tell you that Scala probably has too many features, which is really horrible. I think Martin had yesterday or 2 days ago this figure of the 7 of the abstract data type for the core language of Haskell, which was like only the 7 lambda calculus-like expressions. If you look at all of the expressions that you have to handle when you write a Scala macro, it's actually like, I don't know, 20 or 30 different ones. And that's the reason why we're only translating a subset. And of course, there's some features in the end of Scala that we don't even try to translate because, well, things that you would probably expect, like Solidity is more like a language like C. So we are not trying to translate any generics or something else. It's just in the end only to write really simple programs, but still to on a higher level of abstraction than in Solidity itself, allowing you to have this, allowing you to write the whole program in a single program and not in different parts. There was something else. Solidity has bounds on resources, right? How well do the generated programs run? And that's a good question. And this work in progress, so we're currently still measuring that. And there probably still are some optimizations that you can apply afterwards to make it run faster.
Hi, I'm Sophie. So I've been interested for quite a while in dynamic optimizations and dynamic languages. Now I'm a PhD student at University of Kent, and I'm currently working on phase-driven dynamic optimizations, and that's what I'm going to talk about today. So, but what do I mean by phase-driven optimizations? So let's pick a random application, and let's say you want to observe its behavior over time. And let's say you want to monitor stack depth to do so. I'll explain why later. And so you want to observe the evolution of stack depth over time for this application. And here you can see that, I mean, there's like a really homogeneous pattern going on. So, I mean, it's really quick increase, decrease of stack depth. So that's why it's a big black box. But yeah, so you can see just one clear pattern here of evolution. But if you pick another application like this one, and you still monitor stack depth over time, then you can clearly see that it's behaving completely differently. And here you can see, well, two kind of patterns, actually, this one and this one. And what I've been calling patterns are actually what can be called a phase. So it's a portion of execution time during which the application is displaying an homogeneous behavior regarding whatever metric you choose. So in the first application, you have one phase. And in the second application, you'll have two phases, this one and this one. But why do I care? Well, the thing is, usually, so it's really in general, because there have been work doing exploring other directions. But usually, optimization policies, they are based on fixed thresholds. For instance, for just-in-time compilation, you'll have you'll trigger compilation once you've reached a fixed number of execution of a method, for instance. And well, those fixed thresholds, maybe they're not necessarily adapted, or they're not as relevant or efficient, considering that, well, the application has a variable behavior. And so maybe we could gain something by taking into account this variable behavior in dynamic optimizations policies. And so that's basically what I'm working on. I'm trying to find ways to take into account phased behavior into dynamic optimizations. Okay, so to be a bit more specific, so I've been recently working on a phase-driven garbage collection. So it's really an experiment. It's work in progress, you'll see. So the idea here is to try to trigger collection regarding the phase you're in. And we're using stack depth to do so, so as mentioned in earlier examples. So the idea here is to try to trigger collection when the stack depth is low, because we assume low stack depth means you have like kind of a few live data, and so that we could maybe have a performance gain by doing so. These experiments we have conducted using the second application I've talked about earlier, so which is the half-life benchmark, which has this really clear phased behavior, and to try to see whether it could benefit from having a phased garbage collection. We have tried to trigger garbage collection in between the two phases, so yeah, basically here, where the stack depth is pretty low. So we've done this, and we have, well, the first results. So still, this experiment work in progress. There are still some blank spots in these results that needs to be investigated. But yeah, so the idea is we have run this benchmark for 2,000 iterations, and we have measured the execution time per iterations. And so the blue line represents a normal execution of the benchmark, and the red line, so that you see a bit behind, represent the execution of the benchmark with these GC call in between the phases. So yes, we've introduced a GC call. So the fact that it's, well, in average, a bit slower is not really surprising. But what you can see here is also that, well, the performance profile is, well, it has quite changed a bit, right? Because it's kind of more stable. It's it's less variable, and so maybe that's a good starting point to continue investigating into that direction. So as I said, it's still an experiment, so well, we still have a lot of things to do, among those things, so stack depth is a good starting point, but it's a bit limited. So it was based on earlier work from Wilson, who was using stack depth for garbage collection, but having phase where you could have rich information about allocation, well, could actually guide maybe better the triggers. Something I want to investigate as well for GC or for something else is the fact that phases repeats. So you haven't seen this repetition in my first examples because you only had like 2 phases, but sometimes the phases repeats, and that could be actually really, we could gain something to see, okay, I know that I have this phase A which is repeating 10 times over the whole execution. Maybe I could have something handy that I could apply every time, and maybe I could gain something out of it. The real challenge of the whole approach is that, of course, well, I need to provide phase information. I need to add new decision-making components, and of course that will induce an overhead. And so the big challenge is to try to limit the overhead, as always in dynamic optimizations anyway. And so I've been working on GC for a while, but not only, and if you're not that fond of garbage collection, well, you can say that phases could be applied to something much different from GC. Yeah, for instance, JIT compilation. So I'm just throwing ideas here. But yeah, maybe if you are running your application on heterogeneous hardware, maybe you could use, it could be relevant to use phase information to to determine whether you have to offload a certain type of computation to a GPU or another kind of hardware. I've been working on GraalVM recently, so which is a meta compilation framework. And actually, I think that meta compilation could also benefit from phase information. In which form is still to determine, but I think I'll try to investigate in that way as well. So yeah, I mean, so that was my example about GC, but I think it could be broadly used in different kind of optimizations. And that's all for me. So if you have any questions, I'm happy to answer. Yes.
Nathan, you need to unmute yourself.
Okay, yeah, I thought
the same thing I'm doing every single time, where I've got like the button that glows green, and then I'm like, oh, I must be able to talk now. Have you looked into ARM's big dot little? Like the thing they're doing now, where they have like 2 fast cores and 4 slow cores, they staple them together, and you get a better power efficiency. Okay.
Not yet. Could you point me to anything about this?
Okay.
In the chat or
I just know of a Wikipedia article, but there's like, I guess I have an article on Linux support for it. I know that in Android it's supposed to be a big win, but I don't actually know what the scheduling or anything looks like.
Okay. Do you still have other questions?
No. Whoops.
Okay. Great. Thank you. So I have another question. Which programming language is this GC? So this experiment has been run on the native image of which is given by GraalVM. So we have been running. So we are using the GC of the native, so the substrate VM, which is pretty basic copying garbage collector. And the language we've been using is some custom Smalltalk dialect.